Okay, what we want to talk about now is we want to talk about sinusoidal functions, which is something that we use in electrical engineering, physics, mechanical engineering. It's basically a mathematical curve that presents a smooth periodic oscillation. So what we mean by periodic is a function that has a pattern that repeats as a regular interval. That interval is known as the period, and the function exists for all times. In other words, it runs from negative infinity to positive infinity. Sinusoids often occur in pure and applied mathematics, physics, engineering, signal processing, and many other fields. They describe electromagnetic waves. They describe sinusoidally oscillating voltages, like the voltage that comes into your house. They describe vibrations and many other things that occur in nature. A sinusoid refers to the nature of the oscillation. It's a general term. It typically refers to either the sine or the cosine function, since they're related by a phase angle difference of 90 degrees. So we'll define phase angle in here in a bit. So it's called sinusoid, but it can be either sine or cosine. So in its most basic form is a function of time as given on the next slide. And what we want to do is look at the form, and then we'll talk about a couple of things. Specifically, a lot of times in signal processing, you have within the sine function or the cosine function both degrees and radians. And this is just a historical thing. All right, so in electrical engineering, we almost always use the cosine function to describe sinusoidal oscillations. This is for both mathematical and historical reasons. So we use, the cosine to describe our oscillations. So a typical function looks like this. You have some value A, which is the magnitude or the amplitude. In electrical engineering, we tend to call this the amplitude. In physics, they call it the magnitude. We then have the cosine function, and inside the cosine function as the argument, we have omega t plus phi, where t is a variable. Omega is the frequency in units of radians per second. So notice that omega t would be radians per second times seconds, so this is going to be radians. And then phi is a phase angle or an offset from zero. So phi can be zero, which in that case you would just have f of t as a cosine omega t, or phi can be some value. In electrical engineering, you often tend to see this in degrees. So inside the argument of the cosine function, this omega t plus phi is replacing the x that we were previously using when we talked about the cosine of x. So now x becomes omega t plus phi. Omega is a constant, phi is a constant, t is the variable. So now the variable occurs in time, not in total angle. But we can find the total angle by taking t, multiplying it by omega, and adding the phase shift. So here's an example of two different frequencies on the same plot. We're plotting the cosine of pi t, and then we're plotting the cosine of 2 pi t. So f, which is the blue line, has a frequency of pi radians per second. G, which is the red line, and I need to fix this as well on the graph because G is actually the red line, and it's the cosine of 2 pi t. Then we plotted t and f and t and g on the same plot. And so you can just see the red line oscillates faster. It oscillates twice as fast as the blue line. Notice that they do share some common points at the sort of the repetition time of each of the curves. So they do share some common points. When this happens in electrical engineering, we say these are harmonics. All right, now let's look at the effects of what happens if we shift the phase. So we have two plots here. The cosine of pi t is plotted in blue. The cosine of pi t plus pi over 4. And a little quick quiz, what is pi over 4 in degrees? So we've got cosine, so the frequency is the same, and the red line has a phase shift. Now notice that we added pi over 4. What that does is that shifts the curve to the left, which is a little bit counterintuitive. So it shifts the function to the negative time direction, even though it is a positive phase shift. And if you think about that, since on the time axis, oh, and here's 0 right here. So the blue line, the cosine is 1 at 0. The red line, the cosine of 1, actually occurs when t is negative. That's because we're plotting this versus time, not versus angle. And so remember that as the axis gets more positive, we actually are later in time. And so since we have a positive phase angle, we would expect that peak to occur earlier. So this is just what the effect of a phase shift looks like, once again plotted in MATLAB. Excuse me. All right. So we use sinusoidal functions a lot. One particular application is typical AC current and voltage. Another is we can use them to describe biomedical signals. And so typically we talk about an AC voltage. It typically is expressed in the following way. So here's a typical AC current. We have some V of t, which is voltage as a function of time. We have V sub 0, which is the magnitude, and then we have the cosine of omega, which once again is the frequency in radians per second, t plus phi, which is the phase shift. And once again, we'll talk about why the cosine function is used. It has to do with Euler's relation. All right, some important relationships. So this is a collection of formulas and definitions. The frequency omega in radians per second can be found by looking at whatever multiplies t in the cosine function. The frequency in hertz, also called cycles per second, we can get by taking omega and dividing by 2 pi. So omega is f cycles per second times 2 pi radians per cycle, and so the units should work out. For whatever reason, students have an incredibly difficult time in remembering this. So I think you just have to do the cycles per second times 2 pi radians per cycle in order to get the do you divide or multiply by the 2 pi correct. So use your units to help you remember. F is hertz or cycles per second. Omega is radians per second. So we're taking radians per second, we're dividing by 2 pi radians per cycle, and that should give us cycles per second. The period in seconds is found by taking t as 1 over f. Now, what is the period? The period is the time it takes for the function to repeat itself once. The phase angle is given by phi, and once again, the amplitude or magnitude is what multiplies the cosine function. So, as an example, we might have some voltage defined as 10 cosine of 2 pi t plus 30 degrees. If we wanted to find the amplitude, the frequency in radians per second, the frequency in hertz, and the period in seconds, and the phase in radians. So to find the amplitude, you just read directly from the form of the function. The amplitude would be 10. The frequency in radians per second, look at what multiplies t. It's 2 pi, so it's 2 pi radians per second. The frequency in hertz we would get by dividing that by 2 pi. So the frequency in hertz is 1 hertz, or 1 cycle per second. The period is 1 over the frequency, so it's 1 over 1, or 1 second. And then the phase is given as 30 degrees. If we want to convert that to radians, do you remember how to do that? You divide by 180, you multiply by pi, so basically it would be pi over 6. Now you're asked to find the value of V of t at 1/6 second and at 1/3 second. The first thing you have to do in order to do that is you have to convert your degrees to radians, and then you should just be able to plug in 1/6 for t and then 1/3 for t and get an actual value of what V of t would be. So this is some enhanced derivative and integral formulas for sine and cosine. Once again, these are optional. As far as memorization goes, this is just here to help you in your future classes, as well as if you need a quick and handy reference.